We are now starting on Chapter 4. This chapter is all about two new types of functions. At least they are new to this class, but you probably will have seen them already in an algebra class. We are going to start today specifically with exponential functions. So an exponential function is any function of the form f of x is equal to a to the x power for some number a, which is called the base of the exponential function. Specifically here, we need a to be a positive number aside from 1. We specifically want them to be positive because a negative base would result in a very convoluted domain for the function. Specifically, we wouldn't be able to, say, define the function for x equals 1/2, because then we'd be trying to take the square root of a negative number. But it would be defined for just x equals 1, x equals 1/3, because we can take cube roots, x equals 1/5. All those it would be defined for, but it wouldn't work for 1/2, 1/4, 3/2. It'd be really weird what the domain would be if we included negative numbers. So we are only going to do this for positive a's, positive bases. We also exclude a equals 1 because remember 1 to any power, 1 to the x power, is always equal to 1. So that means if we were to let a equal 1, we just have a constant function. And there's no point in including a constant function in this definition. We wanted this to be its own category of functions and not overlap with the constant functions. Most of all that we're going to learn about exponential functions will depend on what we call the law of exponents. There's 7 of them that we're going to list from the book. They're not really completely separate from each other, but we're going to list all of them just to stay with how the book writes it. So here we're going to say that a and b are positive numbers. X and y are any real numbers. First one, a to the 0th power is always 1. We actually mentioned that. That's why we had to exclude a equals 1. But it is an important law of exponents. Two, if we take the product of a to the x power and a to the y power, the product of two powers with the same bases is the same as that same base to the power of x plus y. So a product on the outside is equal to a sum on the inside. On the other hand, if we, instead of looking at products, we look at quotients, a to the x divided by a to the y, that's the same thing as a to the x minus y. Division on the outside is equivalent to subtraction on the inside. Property 4, if we already have a to the x power, and then we raise that result to the y power, it's the same thing as if we took a to the x times y power in the first place. Number 5, so all these 4 here dealt specifically with the same base in all the cases. Property 5 is going to be a little bit different. Here we're going to have 2 different bases, but we're going to have one exponent. If we take a times b and then raise that result to the x power, it's the same thing as if we took a to the x power and b to the x power and we multiply the results together. 6 is similar to that. Instead of multiplication, though, we're going to do division. If we have a over b to the x power, this is equal to a to the x power divided by b to the x power. And a lot of people, even if they're familiar with exponents, can sometimes forget this one. This helps specifically when you take, say, a fraction squared. You can easily get what that is by just squaring the top and the bottom. Finally, we have a property that's talking about what a negative exponent means. A to the negative x is the same thing as 1 divided by a to the x power. It's kind of more of a definition of what negative exponents mean. Now, One thing to note here is that really 7 is just a consequence of 3 and 1. So if we have a to the 0th power on top, that's just a 1. 1 over a to the y is equal to a to the, 0 minus y, which is just a negative y. That just gives us our property 7. So these are not completely separate properties, but we do want to be able to know all the different things that can happen. Let's work one of the problems just to kind of get used to how all those properties can work together. This is kind of a review, but why not? So problem 3, this is a 4-part problem. Really, it's just four separate problems all in one. They're not really related to each other too much. But the point here is use the properties of exponents to simplify each expression. In A, they give us the expression of 7 to the 5th power divided by 49 cubed. And we want to write this in a simpler fashion. And they want us to do this without using a calculator. We want to be able to figure this out for ourselves. So what's the first thing we can do here? Well, the first thing I would do is we want to be working with the same base if possible. What is a good base to be working with here? We need to recognize that 49 is actually 7 squared. If we already got a 7 for one base, let's convert the 49 to an exponential in terms of that same base of 7. I'm going to write this as 7 to the 5th power divided by 7 squared, which is the 49, but then we need the 3rd power. Now everything is an exponential with a base of 7. And we can go ahead and work with this. Now 7 squared to the 3rd power, remember that is one of the things that we have a property for, property 4. We have a to the x then to the y is equal to a to the x times y. So really we have 7 to the 2 times 3. 2 times 3 of course is a 6. And so that's a lot simpler than we had before. Now of course now we have a quotient of some power of 7 divided by another power of 7. We can use our property 3 and just subtract those two exponents. This is the same thing as 7 to the 5 minus 6 power. Or in other words, 7 to the negative 1. But then the negative 1 here, as we should be well aware of by this point, just means 1 over 7. So this expression here is really just 1/7. That's what it is. Move on to part B. Again, this is not really too much related to part A. We have another expression. We have 9 to the 2/3 power times 3 times 3 to the 2/3 power. And again, we want to simplify this thing. So what's the first thing we can do? Well, once again, we want to use the same base if possible. Really, we want to use these properties here the most of all of them. Of course, it's not that we want to ignore 5 through 7, it's just the 1 through 4 are usually the nicer ones to use. So first thing we want to do is try to find the same base on all of these. And we know that 9 is 3 squared. So if we have a base of 3 on the other ones, we'll go ahead and convert the 9 to a 3 squared. So we have 3 squared to the 2/3 power. That's our first one here. Then we'll multiply that by 3. And we're going to multiply that by 3 to the 2/3 power. Well, 3 squared to the 2/3 power is the same thing as 3 to the 2 times 2/3 power. That will be that first exponent there. But then we also have, this is actually 3 to the 1st power. Remember, everything is itself to the 1st power. So we can go ahead and add these exponents together. So we have a 2 times 2/3, we have a plus 1, and a plus 2/3. That's all these exponents combined. we used multiple properties to do that. We use a combination of property 4 for that first term, but then we use multiple iterations of property 2 to put all those together. Kind of skipping a few steps here, but hopefully we can be okay with that. Now, what is 2 times 2/3 plus 1 plus 2/3? Well, this first term here is 4/3. 4/3 plus 2/3 is 6/3. And because now the numerator is actually a multiple of 3, we can simplify that. 6/3 is 2. And then 2 plus 1 means that we actually have a power of 3 now. That's what all those add up to be. 3 cubed. Maybe you might not know this off the top of your head, but it is 27. It's 9 times 3. So you have to multiply 3 3's together. And that is definitely as simple as we could possibly make it. All right, part C. Here we have 25 to the 1/2 power times 5 squared, and all of that to the 1/3 power. I want to figure out what this thing is. Once again, like the previous two, we want to put everything in the same base. So since we already have a base of 5, it might make sense to go ahead and convert to 25 to 5 squared. So really, what do we have? We have 5 squared. We're raising that to the 1/2 power. And then we're multiplying that by 5 squared. Okay. Well, 5 squared to the 1/2 power. Well, 1/2 power is really the square root, isn't it? So really, as you might expect, the square and the square root should cancel each other out. But the reason they do that is because when we have 5 squared to the 1/2, we end up getting to multiply the 2 and the 1/2 together. That's our property 4. We had 2 here and 1/2 here. We get to multiply those together. We get a power of 1. And so 5 to the power of 1 is just 5. But then we also have 5 to the power of 1 times 5 squared. If we get to add those all together, let me write it this way. We have 2 times 1/2 plus 2 is what we had total. But then this became a 1 plus 2, so a power of 3. We have 5 cubed to the 1/3. But of course, now we get to multiply those together. We have a cube, but we also have a cube root. This is 5 to the 3 times 1/3, or 5 to the first power, which of course is just 5. Last part of this problem, we have a 1/8 to the -3 power. We have a 2 to the -3 power. And we have a 4 to the 0th power. And we want to simplify this one now. Now, like on the previous 3 parts, we have different bases here. So we want to simplify this to one base. We don't really have to worry about the 4 to the 0th power, because we know this is always going to equal 1. That's actually our first property of exponents. So we can kind of ignore that. But it does turn out that we could write the 4 in the best base here. The best base is going to be the 2, because 4 is 2 squared, and 8 is 2 cubed. So that's what I'm going to do. I'm going to turn this into powers of 2. 8 is 2 cubed. Of course, 2 is 2 to the first power. We don't have to do anything there. But I'm not going to bother with the 4. The 4 is just a 1. So I'm just going to put a 1 there, and it will go away in the next step. Next, let's go ahead and simplify things. Remember, this negative power here means that we do flip everything upside down. This is the same thing as 2 cubed, but then we're also multiplying that by 2 to the negative 3 power, and of course the 1 is just goes away. That means we can multiply the 3 and the 3 together, and then we can add that new power of 2, that 3 times 3, to the negative 3 that we have over here. So 3 times 3 minus 3, hopefully you can see that that comes out to be just a 6. We could leave it like this. I think they want us to actually write out this as just a number. We need to know what 2 to the 6th power is, and that turns out to be 64. There's a couple ways you can think about that. You can think about, you could say 6 is 3 times 2, and so really we're talking about 2 to the 3rd power then squared, but 2 to the 3rd power is 8. 8 squared is 64. That's one way you can do it. Or you could just multiply 6 2's together. Doubling things isn't too bad. But the point here is how we take some more complicated expression and turn that into a much simpler power. And it might be in some situations we might not have numbers in here. We might have a variable. If this was x instead of 2's, we could go ahead and still do the same process and get x to the 6th power. Now there's one topic that the book does mention but doesn't really emphasize. It's that the exponential functions are defined for all real numbers. Let's just go ahead and take our exponential f of x is 2 to the x. 2 is kind of the simplest base that we can use. It's very easy to compute this when x is an integer. And we can say 2 to the 1st power is a 2, 2 to the 2nd power is a 4, it's 2 times 2. That's how we normally do powers, right? 2 cubed is 2 times 2 times 2, which is an 8, and so on and so forth. We can even do this for 0 and for negatives. To the 0th power, we already said is a 1. Anything to the 0th power is 1. 2 to the negative 1 power, that just means we flip it upside down. So we get a 1/2. 2 to the negative 2 power, this is 1 over 2 squared. Of course, 2 squared was 4, so we get 1/4. And so on and so forth. Those are relatively painless. For fractional x's, we need to look at roots. 2 to the 1/2 power is the square root of 2. 2 to the 1/3 power is the cube root of 2, and so on and so forth. We can even combine this with the ideas for the integers to look at more complicated fractions. Something like 2 to the 7/5 power. This is the 5th root of 2 to the 7th. Or we can also write this as 2 to the 5th root, or the 5th root of 2 to the 7th power. Either or, they actually give you the same thing. Because this is equal to, you could say, 2 to the 1/5, then to the 7th power, or you could write this as 2 to the 7th, then to the 1/5 power. Because all we're doing is multiplying the 7 and the 1 over 5. But what do we do if we have an irrational exponent? What if we had something like 2 to the square root of 2? Or 2 to the pi power? These should be defined if we're saying that our exponential function is defined for all real numbers. But there's not really an obvious way to approach these. We can't just say it's a root of something, because there's no base here to work with. So there are a few ways to approach it. Probably the best ways is to use some techniques that we haven't really covered yet, and we'd have to take a little bit of a different viewpoint on some of this stuff. So we're going to use probably an easier way to understand it. We're essentially going to use limits. Basically, let's start with the 2 to the pi power. We know that pi is 3.14159 and so on and so forth. I mean, we have infinitely many different decimal places, but at least we know that we have these decimal places. What we can do is we can start by taking some of the decimals and raising 2 to those powers. We can start with 2 cubed. Just take that 3 at the front of it. We have 2 cubed is equal to an 8. We can move on to 2 to the 3.1 power, or 2 to the 3.14 power, or 2 to the 3.141 power, and so on and so forth. You can essentially just keep putting new digits in there as we go. And anytime we have a number that has finitely many decimal places, this really is just a fraction. We basically 3 plus 1/10, or 3 plus 14 100ths, or 3 plus 141 1,000ths. We can turn that into a fraction relatively easily. And so all of these, even if the roots that we have to take are kind of really big numbers that we'd have to put in front of our radical, it's something that we technically have a definition for. It's something that we can wrap our heads around. And so we can go ahead and compute these and get results. So 2 to the 3.1 power is actually 8.57418777, and so on. We put in 3.14 as the exponent on 2, we get 8.815240927, and so on. And using this exponent instead, we get 8.8235333055. Basically, we have the sequence of numbers that is going to actually approach a particular value. The more digits we put in, the better our value is going to be, and it will actually approach a particular number. I mean, we'd have to prove that it does actually approach something, doesn't just keep going off to infinity or something like that, but it does work out pretty nicely. Basically, we want to define 2 to the pi power to be the limit of these things. What number do these go to as we put in more and more digits of pi? And it turns out that is going to be 8.824977 to 8, and so on. So we're actually getting relatively close even at this point. Now, for us, we don't really have to care too much about this process, but it is a way of making sure that we know that there is a value of what 2 to the pi should be. And the reason why we don't have to care about it too much is there's 2 reasons. First of all, there is a much better way of finding these using logarithms later on if we absolutely have to do them by hand. But the other thing is that we do have calculators. We are living in the modern age where we have these handy-dandy calculators to just do it for us. Any scientific calculator should be able to handle irrational exponents just fine. You should be able to take out your calculator, put in 2, there should be an x to the y button or something like that. They might use different variables there, but you press that button and then you put in, there's probably a pi button as well, and then press enter or press equals, and it'll give you this result. So mostly you don't have to worry about these sequences as a way of doing the computations. But just be aware this is how we might think of them being defined. This is how we know that there is some value that makes sense to be put as what 2 to the pi power actually is. This is why we say this function is defined for all real numbers. In later sections of this chapter, we will be talking about exponential functions in applications, and we'll also be able to differentiate them. But for the moment, what we're going to focus on is what the graph of an exponential function should look like. And we'll go ahead and start with that 2 to the x power that we were working with just a moment ago. What should the graph of this thing look like? Well, for the moment, since we don't know really how to handle this using calculus or anything like that, let's just go ahead and make a table. Put different x values. We'll take 2 to the x over here. We'll go ahead and toss in some numbers that we know. For instance, we know what 2 to the 0th power is. We know that to be 1. In fact, the 2 really didn't matter there. We should always have 1 there. If we put in 1, 2 to the first power is a 2. If we put in 2, 2 to the second power is a 4. Go ahead and put in 3 as well. 2 to the third power is an 8. And we can even go the other way. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4, and so on and so forth. So if I go ahead and draw a picture of this, let's go ahead and mark off here. We have 1, 2, 3, negative 1, negative 2, negative 3. We have to kind of maybe shrink our y-axis a little bit. I do want to include that 8 on there. So let's say this is 8 here. 4 is half of that. So do something like that. So we have our various points. We have 0, 1 is that point there. 1, 2 is this point here. We have 2, 4, so 1, 2, 3, 4, which should be about here. Then we said this should be 8 up here, and 3, 8 is a point on our graph. We also have negative 1, 1/2, so kind of put in 1/2 there, get as close as I can at least. And we have 1/4. At negative 3, we should have 1/8. We get really small numbers over here, but they are still positive numbers. That is kind of key. So we have a curve. Let's see if I can draw this nice enough. No, close enough. This is our graph. We have y is equal to 2 to the x power. Let's do the same thing, but for a different base. Specifically, I'm going to take a base of 1/2. So here a is 1/2. It looks a little bit more complicated, but it really is just a number to the x power. Now note that we don't really have to come up with a brand new table of values, because we do have our laws of exponents. 1/2 to the x power is the same thing as 1/2 to the x power, or we can even write this as 2 to the negative x power. In fact, writing this as 2 to the negative x power is pretty handy, because that means I can essentially just use the same table. We still have 2 to some power, but we need to switch our x's. We need to switch our positive numbers for our negative numbers. And that's essentially going to take our graph here and swap our positives with our negatives in terms of x values. The y values are going to be the same thing. So let me try to get a nice graph of this one. Again, let's say that's 8 there, 4. There we go. So we'll go ahead and use the same table, but I'm going to essentially just change the signs over here. So 0 is going to correspond to 1. It's going to be that point there. 1 is going to actually correspond to 1/2 now. 2 is going to correspond to 1/4. 3 is going to correspond to 1/8. And then we can go the other way. Negative 1 is going to correspond to 2. Negative 2 is going to correspond to 4. 1, 2, 3, 4. And then negative 3 is going to correspond to 8. So once again, let's see if I can get a nice enough graph here. It's a little hard to do on a tablet like I'm doing. So I'm trying to draw on the screen while my pen is actually on a different surface. There we go. Well, that's good enough. That is our graph. Now we could go ahead and use GeoGebra to graph these more precisely if we wanted to. But the point is that we want to get an idea of what these graphs should look like by hand. We want to have an idea of what these graphs are really doing, rather than just, well, I slap a picture in front of you and call it good. But the point here is that these are our two typical graphs. Every graph of an exponential is going to look somewhat similar to these two. Now, there's of course, there are going to be some differences. In fact, most of our differences really will come in a sort of a scaling factor to these. But they'll be looking like one or the or other of those. Specifically, let's look at f of x equals a to the x. Remember, a here has to be a positive number aside from 1. And we're going to split this into two different cases. We'll have when a is greater than 1. In this case, our graphs are always going to look similar to the graph of 2 to the x. I mean, 2 is in this category if 2 is greater than 1. These are always going to look like this. Oops. Let's do that. Okay. There's two key points on here. We're always going to have 0, 1 is always going to be a point on here. We're also going to have the point 1a is always going to be on there. So just like we had 1, 2 on the graph of y equals 2 to the x, we always have 1 comma whatever our base is on there. I usually go, when I'm asked to graph something like this, I'll usually go ahead and identify those 2 points and use those to give myself an idea of how big or small things should be. In the other case, when a is less than 1, but it is still going to be a positive number, we're going to be the same as the 1/2. We're going to have something that looks like this. Again, we have two particular points on here. We have 0, 1, and we also have a point over here of 1a. Remember, a here is less than 1, so that it is a lower point than it was over here. Here, a was bigger than 1, so it's higher than the point at 0, 1. Here's the other way around. So actually, if you graph both of those 2 points, it should pretty much tell you which case you're in. Because this one, it has to be going up. This one, it has to be going down. And those 2 points tell you that very explicitly. Now, there's a few key features to this. First of all, the domain is all real numbers. Let me write that as negative infinity to infinity. Domain is everything. We already wanted that to be true. But if you remember what the graphs look like, it can be kind of reinforce that idea. These graphs definitely will cover the entire x-axis. On the other hand, there's the range. Usually range is a little bit hard to identify for just a random function out there. But in these particular cases, it's actually quite important. Specifically, note that our graph is entirely above the x-axis. There are no y values next to our graph that are negative. There's no negatives. In fact, there's no zeros. It never hits the x-axis at all. There's no x-intercepts here. So the range is only going to be positive numbers. It's going to go from 0 to infinity, not including 0. That's actually a pretty key fact, and we're going to be making use of that a lot when we get to logarithms as well. 2. We have no x-intercept. We already mentioned that, but I'm going to reiterate it here. Never hits the x-axis. And the y-intercept is always the point 0, 1. Three, we can say this is continuous. It's always continuous. So that's something that we kind of haven't proven in any way, shape, or form right now, but it is actually true. There's never any gaps, no jumps. This is just a continuous line all the way from negative infinity to infinity. These are the properties that are true for both cases. On the other hand, for these two different cases, we have For a greater than 1, it's increasing always. We already kind of mentioned that here, that it definitely has to go up from 0, 1 to 1a, but it always goes up. There's no point on this graph ever that it doesn't increase. On the other hand, if a is less than 1, it's always decreasing. There's no point where it doesn't decrease on this graph. Kind of want a little bit more room to write out the next statement. So I'm going to have to write this on the next page. So property 5, we're going to have two cases. For a is greater than 1, and for a is less than 1. We're going to have limits. Specifically, we're going to talk about the limits at infinity and negative infinity. What happens to these graphs as x goes to the extreme values? Well, in the case where a is bigger than 1, as we let x go off to infinity, this just continues to increase. It never comes back down. In fact, it never kind of settles down anywhere either. In fact, it even just keeps growing faster and faster and faster the further out we go. This function, when a is bigger than 1, definitely is going to infinity. On the other hand, when we go the other direction, now kind of ignore my drawing here. It kind of looks like it went up a little bit there. It is still going to be decreasing. In fact, it decreases more and more and more. It never quite reaches 0. It never hits the x-axis. It's going to decrease down to 0. In another way of putting that, we do have a horizontal asymptote of y equals 0. But it's only on one side. Unlike our rational functions, we have a one-sided horizontal asymptote. Now, for a less than 1, those two are flipped. When we're going to negative infinity, it goes to the function is going to infinity. When we go to positive infinity, our function is going to 0. So these are the other way around this time. So kind of swap those. Those are the key features of an exponential graph. We can also use those ideas as a baseline along with transformations to graph functions based off of exponential functions. So let's just take a look at a couple of those kind of things. Let's look at problem 12. Here we're going to graph the function y is equal to 3 to the x plus 2. Notice that this is not technically an exponential function according to our definition. It doesn't just have x as the exponent. This is not sum based to the x power. This is just a little bit of a how do I want to put it? Let's just say it's a function that's derived from an exponential function. But the point here is that there is an exponential function that is the base of this. It is, we want to think about what is 3 to the x power. If we graphed y equals 3 to the x power, what should this thing look like? Well, remember, I said there's the way I like to do it is I like to pick some points. We specifically have the point here at 0, 1, and then I want to graph what happens at 1. When I put 1 in here, I get 3. So let's say, come up here to about 3. This is 1, 3. You can even go the other way if you want to. So at negative 1, we get the point of negative 1, 1/3. But the point here is our graph. I don't want to cross that x-axis, but want to graph something like that. Now that is the graph of y equals y equals 3 to the x power. What does putting the 2 in there do? Well, when we add 2 to the inside of a function, it causes the graph of that function to be shifted to the left by 2. Basically, what's happening at -2 should play the role as if I plug 0 into this function. If I put -2 in for x, it will be the same as if I was plugging 0 into the function 3 to the x. So I'm going to take this function here, and I'm going to just shift it all over. Maybe even let's go ahead and even just put it in here. We're going to take every point in here, I'm going to shift it over. So 1, 3 is going to be shifted over to -1, 3. 0, 1 should be shifted over here to -2, 1, and so on and so forth. But it'll have the same shape to it. It's just now located in a slightly different place. Everything was just moved over by 2. And now this is the graph of y equals 3 to the x plus 2 power. What about problem 17? Here we have, so they changed the letters on us here. We have s of t is 1/4 times 3 to the -t power. Now note here that we can actually do we can use some properties of exponents here. 3 to the -t power is really the same thing as a 1/3 to the t power. Basically, we have a base here that is less than 1. We do have a multiplier out in front, but for the moment we're going to ignore that. We're going to graph this function here, this 1/3 to the t power. That is an exponential function. This time I'm actually going to graph it a little bit bigger so I can, because that 1/4 is going to make things small eventually. I'm going to start with some points. First of all, when I'm graphing, so let's even just go ahead and label. We're going to have y equals 1/3 to the t power, or let's even just say to the x power. That's what we're graphing here. We definitely have a point of 0, 1. That's always going to be on an exponential function. I'll go ahead and graph what happens when I plug in 1. I just get a 1/3. So I have a 1/3 over here. 1, 1/3. And here's why I like to graph the 1 at -1 as well. Because I've put -1 in here, I'm going to get y equals 3. Actually, maybe I even want to move the label here out of the way a little bit. So at -1, then I want to go up to 3. So 1, 2, 3. I'm going to have my graph that goes through these. Something like that. Okay, what does the 1/4 do? Well, multiplying the outside of a function by a number either stretches or shrinks this vertically. It stretches if we multiply by a number that's bigger than 1. So if you say double it is going to make all our y values double what they were without changing the x values. But putting a number between 0 and 1, like a 1/4, will take all of our y values and shrink them down to 1/4 what they already were. We're going to have the same x values though. So 0, 1, we're still going to have a 0, but now we're going to have 0, 1/4. And let me put it down here. 0, 1/4 is that point there. At -1, instead of having a y value of 3, it's now going to be a 3/4. It's actually lower than this point over here. So we have -1, 3/4. Instead of 1, 1/3, the 1/3 is going to be multiplied by 1/4. 1/4 of 1/3 is 1/12. Things here maybe not quite perfectly to scale, but hopefully you can see why I'm having trouble drawing things to scale here. But we actually have pretty small numbers here. But the point is that we're taking this thing and this this original graph, and we're just kind of squishing it. And we're going to get a graph that looks something like that. This is y equals 1/4 of 1/3 to the x power. Now, I went ahead and changed the variables, so you could write this as s equals 1/4 of 1/3 to the t power. But the graph would look the same way. But that's how we would graph these particular kinds of functions. All right, so hopefully that kind of at least jogs your memory. You've probably seen a lot of this already before. It's kind of a review. Next section, we will actually start talking about the specific base that everybody's more familiar with, or at least hopefully you've seen before, but the one that we're going to be using more often from this point forward, because it's actually a little bit more useful when it comes to calculus. But that's what we have for now. So I'll see you guys in the next video.